Hello everyone and welcome to EET1011. This is the lecture for chapter 9, Kirchhoff laws. Topics that we're going to cover in this chapter will be the Kirchhoff's current law, or also known as KCL, the Kirchhoff voltage law, also known as KVL, method of branch current, node voltage analysis, and method of mesh current. Let's get started with the Kirchhoff current law, or KCL. What this law says is that at any given point on a circuit, mostly known as any node in the circuit, the sum of the currents entering that point must equals the sum of the currents leaving that point. If that doesn't happen, then that point or that node will be accumulating charge, and this will reduce or obstruct the conducting path of current. Or we can also state that current in must equals the current out. If you look at this node right here, let's assume this is the point in a circuit, and we have current A coming in this way, current B coming in this way, so the sum of these two must be equal to the current C that comes out. We have 5 coming in and 3 coming in, so the total of current coming out must be 8 amperes. So if we look at this example right here, this circuit, we can observe that if we take, for example, the node at point C, we have this current, the total current, 6 amperes coming into this node, and then we have the current 4.5 going out, as well as current 3 is going out. So the total current must equals the total current that comes into node C must equals the current leaving the node, which is I3 and I4 and 5. It will be the same if we look at this. Let's see the node here, or node D, right? What coming into node E would be the 2 amperes here from current 3, and this current, which is named current 4.5, is also coming into this node, and then we have a current going out this way, which is the total current again, right? So KCL states that for any node on the circle, the amount of current coming in must equals the amount of current going out. So again, in this example right here, this current 4.5, which is the current that leaves this node in this direction and enter this node in this direction. Notice that this is the same current that goes around this loop. Okay. So on the top we have that the current, total current that comes in here, the IT minus I3 and I4.5 must equals to 0. So at either point C or D, the sum of 2 amps and the 4 amps branch current must equal the 6 amp of total current. So we have total current going in this way, so we have 6 amps, and we have 2 coming out this way and 2 going out this way. So the total current coming in equals the sum of the currents going out. On node D, we have 4 amperes coming in from the right and 2 amperes coming in from the top. Therefore 6 amperes must go out this way, which is the total current again. Kirchhoff voltage law, or also known as KVL, is similar to the KCL, except that in this case we look at the loops in the circuit. A loop is a closed path in any circuit. Okay, and the Kirchhoff law of voltage, or voltage law, KVL, states that the sum in any given loop, in any given closed loop on a circuit, the sum of all the voltages around the loop must equals to 0. So this is one loop, here is another loop. Okay, we can also take this one as one big loop, like that. That will ignore this resistor right here. It will just take the voltages across all the components around the loop. And either way, this loop or this loop or this loop, the total voltages around the loop must add up to 0. Let's take a look at what happened here. We have a source of 240 volts, and if we take a look at this, at the first loop, let's call that one the first loop. Okay, we will go here and we say we have 240 volts, and then in here we have a drop of 30 volts. On this other resistor we have another drop of 120 volts, and in here we have a voltage drop of 90. So we have, if we take this path, the current going into this way, let's assume that when whatever component the current hits and enters, we're gonna take that sign either positive or negative as the voltage. Okay, so if we go in this direction clockwise, the current would be entering the voltage source on the positive, so that would be a positive voltage. So we would have 30 minus, 240 minus 30 minus 120 minus 90, that should be equals to 0, which stays right here. See that? The 90, 120, and the 30, which are the voltage drops across the resistors on this specific loop, must add up to the source, which is 240 volts, stated right here. And if we take a look at the second loop, the loop from C to E to F to D back to C, in other words, this loop right here, if we take a look at these voltages, also we can say that the voltage on resistor 3 or V3, the voltage on resistor 4 or V4, and the voltage on resistor 5 or V5, that the sum of all these three voltages must add up to 0. So if we go, let's say we go around the loop in a clockwise manner. Okay, so we go in here, we're gonna enter this on the positive side, so that we can say that this is a positive V3. It will be positive V3, like stated right here on the formula. And then we continue in this loop. Now we're gonna enter this component on the negative side, so we can say that this is gonna be a negative voltage of 40 degree, or V4, so that will be negative V4 right here. And as we continue on the loop, we're gonna enter this other component on the negative side of the polarity, so this would be also a negative value of 80, which is a negative V5. So we plug in the values, will be negative, it starts from here, negative 40 minus 80, and then in here would be plus 120. If we add up all this together, we get 0. Okay, so that's what the Kirchhoff voltage law, or KVL, says, that the sum of all the voltages around a loop on any closed path in a circuit must add up to 0. So if we take a look at this, let's say we do this loop, okay, the big loop right here. Let's see if that add up to 0 as well. Okay, so now if we go in clockwise, we can say that this is going to be 240, then minus 30, that's 210, then minus 40, that would be 170, then minus 80, that would be 90, then minus 90, that will give you 0. Okay, so if we can take this loop around the outer loop, so we must ignore this one right here. Okay, so the point is that every single loop, in every single loop, the sum of the voltages must equal to 0. Okay, it will be one loop, second loop, or we can also have a third loop, which is the big one around the edge of the circuit. So the method of branch current is basically an application of Kirchhoff's law to a circuit when we have two sources. If you notice on the previous examples, we have a circuit that only had one source of voltage. In this one we have two different sources, so we can calculate the branch currents as well. Okay, so in here what we do is that we still do the loops, but then when we apply the voltage, the Kirchhoff voltage law, we will represent the voltage in terms of current times resistance. For example, the voltage 1 will be the voltage on resistor 1, so the voltage across this resistor right here. We can write this, instead of saying VR1, we can say that this is equals to the current going through this resistor times the resistance on the resistor. So the current times R1. The voltage on resistor 2, we will write it as the current times the resistor 2. And the voltage on resistor 3 is the same as the current 3, which is the current on this resistor, times the resistance of the resistor. Okay. However, the current 3, which is the current going down this way on this branch, is a composition of current 1 plus current 2. If we recall the Kirchhoff current law, or KCL, that says that for every node or any point on the circuit, the current coming into the circuit must be equal to the current leaving the circuit. Okay, so in this case we have I1 coming in, I2 is coming in, so I3 must be going out. Okay, and I3 must be equals the currents that's going out must equals the sum of the currents that are coming in. So if I3 is the only one coming out, and I3 is going out, and I1 and I2 are going in, so we can say that the current 3, or the current on this branch, or the current going out of this node, is equals to the two currents going in. So we eliminate the use of I3. Instead of I3, we can use I1 plus I2. Okay, so instead of I3, we will say I1 plus I2, because the purpose here is to develop two equations. We have two loops, and we're going to have two equations, and we can only solve the system of equations of two equations if we have two variables. So if we keep I1, I2, and I3, now we will have three variables and only two equations, so that will be impossible to solve the problem. Okay, so back to this method of branch current. On loop 1, which will be the loop right here, the first loop, we have the sum of the voltages must equals to 0. So we have 84, then minus, because if we go in this direction, we're going to be entering here on the minus side of the resistor, or the voltage on this resistor. So that would be 84 minus the voltage on resistor 1, and if we keep going around the loop, then we're going to hit the minus of the resistor 3, so that would be minus the voltage on resistor 3. Okay, and those are the only three voltages on this loop, so the sum of all these three voltages must equal to 0. If we follow the direction of the current on this loop 2. Okay, now we see that we're going to have in here, if we go this in this direction counterclockwise, we're going to be entering the positive side, so we'll say 21 minus the voltage on resistor 2 or VR2, and then minus VR3. These three items must equals to 0, as well as the ones on the loop 1. Okay, so what we do now is this: we have a VR1, VR3, and VR2. We have two equations, but we have two equations and we have three variables. So it is impossible to solve this system of equations, at least at our level. So what we're going to do is we're going to eliminate one of these variables, but we're going to replace the voltages. Instead of voltage, we're going to write the voltage in terms of current times resistance. Okay, so for voltage VR1, we're going to say that this is the current 1 times the resistor 1, which is this current right here, current 1 times the resistor 1, which is 12 times I1. At this point, we don't know I1 yet. For resistor, the voltage on resistor 2, the voltage across this resistor, instead of VR2, we're going to write the voltage in terms of the current and the resistance. So we multiply the current on resistor 2 times the resistance on resistor 2, and that will be, the resistance is 3, but the current we don't know it yet, so we're going to write it as 3I2. And the voltage on resistor 3 or VR3 is going to be equals to the current on resistor 3 times the resistance. So the resistance we know is 6. So it's going to be 6 times the current on resistor 3, but instead of writing I3, we're going to write I3 in terms of I1 and I2. So the current 1 and the current 2 are the ones that go into this node, and then the current 3 is the one that leaves the node, right? So this I3 must be equals to the sum of I1 and I2. So instead of I3, we're going to say this is going to be I1 plus I2. Okay, so then we're going to substitute these values in the voltage equation for loop 1. So remember, this is the loop 1, this is the voltage equation right here. So instead of VR1 and VR3, we're going to put in VR1 was 12I1, that goes in here, and VR3 is now 6 times I1 plus I2. We distribute this 6 in this parenthesis, and we simplify this equation, and we end up with a very simple equation that says negative 18 times I1 minus 6 times I2 equals negative 84. That is the equation of loop 1 in terms of the currents. Also in loop 2, we're going to plug in the values of the equations on loop 2. Let's go back to the equation for loop 2. This is the KVL, Kirchhoff voltage law equations of loop 2 from the loop that goes in this direction. Okay, so we have 21 minus VR2 minus VR3. Instead of VR2 and VR3, we're going to write this same equation but in terms of the currents. Okay, so it's right here, 21 minus 3I2, which was the voltage on the resistor 2 right here. It was the current 2 times the resistance, which is 3, and then minus 6 is the resistance times the current that goes through here, which is I1 and I2. So when we simplify this and distribute this negative 6 in this parenthesis, or in other words multiplying the 6 times I1 and I2, we're going to simplify this equation to negative 6I1 minus 9I2 equals negative 21. Okay, so So I'm sorry, this equation right here, the one in the bottom is the equation for loop 2 after we simplify, and the one on top is the equation that we got from loop 1. Okay, so these are the two equations. Now we have a system of two equations, and we only have, this time we only have two variables, which is possible to solve. Okay, two variables and two equations. Then we can use the techniques that we learned in algebra. We can use the process of elimination, so we can use the process of substitution as well. So let's see if we divide the top equation. Let's say divide this equation by -6. We end up with, just to simplify this equation, divide this by -6 and divide this one by -3. We can reduce this equation to this value. Now we have only positive values. Okay. All we did here was, from here to here, the only thing we did was simplify the equations, okay, and reduce the values, the coefficients, and also get rid of as many negative signs as possible. So everybody was negative in here, so we can change the sign on both sides of the equations, and that would not be a problem. So these two systems are exactly the same. So when we solve this system of equations, we find that the I1 equals 5 amps. Okay, so that would be the current going in here. That would be 5 amps. And now that we have I1, we can substitute this I1 into either one of these two equations. Well, let's take the one in the bottom, and now we say this is 2 times I1, but since we already know that I1 is 5, so it will be 2 times 5 plus 3i2 right here equals 7. So from here we can solve for I2, and then we end up with I2 equals -1 amp. Okay, so that means that the current that comes in here is 5 amps, and the current that comes from here is -1 amp. So 5 amp plus -1, that means I3 must be 4 amps. Okay, now what's the negative means on current I2? Because we determined that the current is going this way and we end up getting a positive value. What that means that in reality the current 2 is actually going in the opposite direction. Okay, so we will have that we have 5. In reality, this one is coming in, and then 3 and 2 are going out. But since we stated that we're gonna have our current in this direction, so the value for the current in this direction would be negative, meaning that in reality it's going in the other direction. Okay, so if we want to keep it like from right to left in here into the node, then it's going to be a negative value. But if we say let's change it to go out instead of in, then the value would be positive because it's going in the direction that we said. Okay, so remember, the negative value that you get on the current after solving the equations, if you end up with a negative value, that simply means that the actual current is flowing in the opposite direction than what we said it was going to go. Okay, so to calculate the voltages, the voltage drop around these the circuits. Okay, we have the voltage, we have the resistors, and now we found the currents. All right, so we already know the current 1, the current 2, and the current 3. So to calculate these voltages right here, all we have to do is plug in the values in the formula. VR1, the voltage on resistor 1 is going to be I1 times R2. I mean I1 times R1, and that will give you 60 volts. Then I do the same thing for the voltage across resistor 2 right here, and that will give you 3 volts. And the voltage across resistor 3 will give you 24 volts. Okay, So in here now we see that you can actually go around the loop again and you say 84 minus 60, then minus 24, that would be 0. If we go this way, you say 21 minus 3, that would be, let's see, 21, now I know this is 24, yeah, this is gonna be 3, it would be negative 3, right, because remember that the voltage, the current in this direction is negative, so negative 1 times 3 will be negative 3, so 21 minus 3 plus 24, that will give you a total voltage of 0, okay, because the sum of all the voltages in any given loop must add up to 0. Now notice that the VR3 and VR2 have opposite polarities in loop 2, okay. This results in minus 21 for V2. This one right here. Okay. So this one, we can actually keep the polarities the way they are, just that in here you're going to have plus, in here you're going to have minus, and in here you're going to get minus 2. But this is going to be minus a negative value, because remember the current in this direction is negative, so it's going to be minus 3, so that will be plus 3, and this is going to be minus 24. So 21 plus 3 is 24, minus 24 equals 0. Just be careful with the signs when you're working with these equations, right? Checking the solutions, you can just always plug in the values on each resistor and calculate the current and the voltages on each resistor to verify your solutions. And so the node voltage analysis is a principal node is a point where 3 or more current divide or combine other than the ground. Now let's see an example so we can get a better idea. If we're going to use the node voltage analysis, so what we need to find is the voltage on this node, okay? So if we take a look at this loop right here, if we go from here, you have 84, and then some voltages drop across this resistor, okay? So from 24, we're going to subtract this amount, and this is going to be the voltage that's going to be at this node, okay? And that would be the same voltage going through this resistor. The current goes through the resistor will generate a voltage drop equivalent to this node right here. So if we say that the current I1 is going to be then the voltage across this divided by the resistance. I2 is going to be the voltage across this divided by the resistance. So I3, it will be the voltage on this node divided by this resistance, which we already know that if this is a voltage, this voltage here is grounded this way, so all these voltages drop across this resistance, this resistor. So the voltage N should be equals to the voltage R3. So again, at the node N right here, we can say that in this case, for example, we have I3 going in, so this I3 must equals to the sum of the currents going out, so it would be I1 plus I2, so I1 plus I2 equals I3. Or we can also write this in terms of voltage and resistance. Instead of the current, we can say that the I1, which is the voltage on I1 divided by R1, plus the voltage on R2 divided by R2 equals the voltage on R3 divided by R3, but the voltage on R3 is the voltage on the node N. Okay, and from this equation we can solve for Vn, and then we find the voltage on that node. If we have some values here, we can always solve the problems in that way. Okay, so here's this solution. So this node equations and the loop equations. Okay, so remember, the node equations and the loop equation are the equations that we end up getting when we apply KVL or KCL respectively. So if we want to analyze the circuit from a node point of view, okay, we're going to use the currents going in and the current going out, and then we write the currents in terms of voltage divided by the resistor. If we're going to do the other way, which is the let's see, if we do the KCL, okay, we're going to write the equations of the loops. Okay, we take the loop 1 and the loop 2, and then these voltages must add up, all the voltages around the loop must add up to 0, and then we write the voltages in terms of the current and resistance. Either way, we should be getting a system of equations that is the number of variables is equals to the number of equations. Okay, make sure that if we have 2 equations, we can only have 2 variables to solve for. If we have 3 equations, then we must have 3 variables, and typically would be the currents. All right, so and here in this section right here, you know, is the is showing the steps to follow. If we're going to use the node equation, then apply KCL to currents in and out of the point or node. So the currents are specified then in terms of V over R. Okay? So the equations of currents can be solved to find a voltage node. Okay, so if we do the KCL, we're going to do the node equations. We're going to use KCL to find the currents going in and out of the node, and then we write the currents in terms of the voltage and the resistors, and then we will find the voltages this way. If we use the loop equation, then we have to remember that the KVL, okay, Kirchhoff's voltage law, says that the voltages around any given loop must add up to 0. So we write the equation for the loops, then the equations then the voltages, we will write them in terms of the current times the resistance, and then solve for the current in this way. Okay, what is the method of mesh currents? A mesh is the simplest possible loop in a circuit. So, and then, you know, once you determine those loops, then we can apply the KVL. So here's a mesh, here's a mesh. Okay, so meshes are the simplest loops in each circuit. So in this case, we have a circuit that has 2 meshes, mesh A, mesh B, and then we can do the KVL, which we say all the voltages around this one will add up to 0, and all the voltages around this loop or mesh will be also 0. This will be the current A, this will be the current B. So the voltage here, for example, will be this 84 must equals the voltage drops around this right here. We have voltage, the current in this loop, okay, the voltage on this VR1 should be IA times 12 volts, and the one in here must be R3, which is 6 ohms, times IA minus IB, because one is going this way and this one is moving this way. Okay, when the currents are going in different directions across a component, then the actual current that goes through here is the difference between the two. That will be A minus B. That's why we end up having here 18A minus 6B, because A will be 12 plus 6, that's 18, and then on this one we have minus B, so 6B. Okay, and this will be the equation for this loop using the mesh current. In here we have the current for this mesh as well. All right, so we will have Negative, if we go this way, it's going to be negative 21 most equals to this one right here. So IB will be 6 and 3. That would be 9, but then we have IA going this way for this one right here, then would be minus 6 IA. And this would be the second equation. From this point on, it's just a matter of solving these equations to find the currents on each one of the meshes. Okay, so mesh A gives you this equation right here, and mesh B gives you this equation. If you solve the system of equations, you end up with IB being 1 ampere and IA being 5 amperes. So the current that goes through here is going to be IA, and that would be 5 amps. So 5 times 12, that would be 60 volts. Now in here we have IA minus IB. So that will be 5 minus 1, that will be 4. And 4 times 6, that gives you 24 volts across this one, which makes sense. We have 60 here and 24 here, that's a total of 84 volts. Same we do over here, okay. IB times R2, that will be 1 times 3 will be 3 volts in here. But in here we already determined that it's 24 volts. So that will be 24 minus 3 will be 21. Okay? So it's also here, okay? This is the equation. So if we just plug in the values for IA and IB, that we will get the negative 21. Alright, so this is the end of this chapter. Hopefully everybody do well in the exam. The exam, remember, is going to be on chapter 7 and chapter 9. And thank you for your attention and the opportunity to serve you. We will see you in next lecture.